If you spent time in a high school chemistry lab, you likely remember tasks like trying to titrate acetic acid in a beaker of vinegar. You might also remember receiving a prepared aqueous sample from your instructor and using a rigid scheme to identify which basic metal ions were hidden inside it. Performing these highly structured laboratory exercises builds a very specific and highly misleading mindset about what the field of chemistry actually is. Following a printed lab manual step by step to arrive at a predetermined result is chemical analysis. It is the routine, daily application of an already established method. The overarching discipline of analytical chemistry is entirely different. It is the science of inventing, testing, and validating those very tools and methods before they ever make it into a manual. There is a sharp distinction between the physical act of running a routine sample and the intellectual, iterative act of designing the experimental architecture that makes running that sample possible. Almost all chemists, regardless of their specialty, make qualitative and quantitative measurements on a daily basis. So why do we classify analytical chemistry as a completely distinct branch of the science? The distinction exists because the analytical chemist's job is pushing the boundaries of what can be measured in the first place and determining exactly how accurately it can be measured. Doing that requires extending established methods to completely new, untested types of environmental or biological samples. To understand this field, you have to transition from being a follower of chemical recipes to an architect of chemical measurement. We start with qualitative analysis. This is the process of determining a simple binary. Is a substance present in a sample, or is it not? Merely answering, "Is it there?" rarely provides enough information to solve complex, modern problems. This flowchart maps quantitative analysis, the focus of modern analytical chemistry. Notice the primary split. It breaks down into classical or instrumental techniques. Regardless of the branch, quantitative analysis answers the crucial question: exactly how much substance is present? Detecting a trace amount of boron in a municipal water supply is an interesting data point. Knowing the exact concentration is required to determine if that water is safe to drink. Consider biological samples. Almost all samples of human blood serum contain albumin. Because its presence is universal, the only valid scientific question is the specific quantity. Establishing these exact amounts dictates whether an environmental remediation effort begins, a medical intervention is ordered, or a new public policy is drafted. Because regulatory and safety decisions hinge entirely on precise numerical thresholds, quantitation is the engine driving the entire field forward. Analytical methods are not static constants. They are born, they are adopted by laboratories, and eventually they die. Any given method moves through a strict 7-stage life cycle. Stages 1 through 3, conception, demonstration, and establishing capabilities, are the exclusive domain of the analytical chemist. At stage 4, widespread acceptance, it enters the public domain. Take a mining engineer tasked with evaluating the profitability of an ore deposit. They estimate the value by running an accepted test on an ore sample. In this scenario, the mining engineer acts as the chemical analyst, applying that accepted stage 4 method day after day. The analytical chemist is the person who faced the original challenge of validating that ore testing method years prior. Looking at stages 5 through 7, we see the eventual obsolescence and death of the method. Methods die because continuous development yields newer, faster, or more accurate techniques that outcompete them on the open market. This life cycle forces the discipline to constantly iterate. There is no endpoint where we simply run established tests forever. An analytical chemist provides value by anticipating the obsolescence of current technology and designing the methods that will eventually replace it. How does a theoretical physical observation, like a liquid flashing into vapor, become a legally defensible test for public water safety? This chart breaks down the solution. To prove a result, a chemist must move through 4 rigid levels of analytical methodology. The first tier is the technique, the underlying physical principle. Here, it's graphite furnace atomic absorption spectroscopy. The second tier down is the method. This applies the technique to a specific analyte and matrix. Notice the split. Testing for lead in soil requires completely different steps than testing for lead in water. Below that is the procedure. This tier provides written, step-by-step directions. Organizations like the American Public Health Association, or ASTM, write these procedures to ensure different labs get uniform results. Finally, we reach the bottom, the protocol. This is a set of strict guidelines that must be followed without exception, typically mandated by a regulatory body. In this case, the EPA dictates the protocol for drinking water. Any deviation at the protocol level renders the data legally useless, no matter how sophisticated the underlying technique is. Analytical chemists must navigate this entire hierarchy to ensure a physical principle can stand up as empirical proof in a court of law. Analytical problems rarely originate in a vacuum. They come from pressing civic or scientific questions. A local government might ask, does emission testing actually reduce air pollution? A pediatrician might ask, is dust ingestion a quantifiable hazard to children? The chemist's first job is translating these vague questions into precise parameters for measurement. We handle this translation using the analytical approach, which operates as a continuous 5-step feedback loop. Taking the actual measurement at step 3 is only a fraction of the work. The critical moment happens at step 4, evaluation. This is where the data is analyzed to see if it actually answers the original problem. Evaluating the data often exposes limitations in the current technique, forcing the chemist to loop back to experimental design and try again. This constant evaluation of accuracy, precision, and physical limitations is why statistical analysis is a massive component of the discipline. Calibration and error propagation provide the rigorous statistical foundation required to prove an experimental method is performing accurately. Analytical chemistry is the essential engine of empirical science. It ensures that when humanity asks a vital question, the tools exist to provide a definitively proven answer.